Okay, so for this video, we're going to be tracking down some issues that I've noticed with our setup. So pretty much what was going on was I was going through the book and trying to get all the different discharge behaviors on the output of our secondary and was having a little bit of difficulty. So I started to do more analysis into our system and I noticed some imperfections with what was going on. So I have the system a little bit disassembled right now, but I figured now would be a good time to stop and just kind of start recording what's going on and show you what I'm looking at so we could see, what's going on inside the system and try to track down where those imperfections are happening. So I'll get into first kind of what I noticed, and then we'll start trying to track down where that sort of area is creeping in. What I'm going to do is I'm just going to turn up the voltage enough to just get a break. And I have the scope here set to the single trigger mode. So it's basically just going to take a little snapshot of the oscillating circuits as soon as we turn this on. So I'll just turn up the voltage until we get a break across the spark gap. And we'll get a snapshot of that first oscillation that occurs in the circuit. So I'm going to turn it up here. Okay, so that is pretty much what we have going on in our circuit. Now here is where the problem comes in. Based off the frequency that I would expect this thing would be resonating at about right now with our primary inductor and our capacitance, I would expect this thing to be somewhere in the ballpark of like 500 hertz, high 400 hertz. But what we're seeing is primarily our energy is focused at about here 7-ish megahertz. Let's see. I'm just using the cursors and looking at the frequency. You can see here there's a frequency corresponding to this period here set by the cursors. So you can see that my what I'm thinking is happening in the circuit is not actually happening. So something is not right, because I would expect our oscillation frequency to be much, much lower. And you can see, if let me do another snapshot here. You can see that we do have energy at the expected resonant frequency of our tank circuit here, which is approximately 500 kilocycles. But the energy at this higher frequency is actually much stronger. So now let's look at, we'll do another snapshot with it zoomed out. So let me zoom out a little more actually. There you go, I'll do another snapshot. What we have here is this high frequency is kind of overlaid on top of a lower frequency. So we can see here that we have this little sinusoid shape, which is high frequency is overlaid on top of. So what I'm going to do now is try to drag the cursors around to find approximately what the frequency is at. So I'm just looking at this shape here, where we have it going up and down and up and down. And we have all this high frequency stuff overlaid on top of that. But you can see here that this corresponds to about 500 kilocycles, which is what I would expect our primary circuit would be oscillating at. Now you can see that a lot of the energy is actually not at this frequency. It's at a much higher frequency. So I basically want to go and track down what is actually happening. Now, I do know that when you use spark gaps like this, you are going to get some upper harmonics overlaid on top of your signal. But is it this bad? I don't know. This seems like most of the energy isn't available to us because it's just such a high frequency compared with what our secondary is resonating at. So all the energy we're dumping into this primary, only a small fraction of it is actually going where we want it to. So that's kind of what we're going to be investigating, is where is all this high frequency coming from? So pretty much when I first started thinking about how to approach this, my thought process is that, ideally we want all the energy just kind of going in between the capacitor and the inductor once our spark gap breaks. But we have all this extra stuff attached to this resonance circuit, which might be affecting it in different ways. So my first idea was just to try to isolate the resonance circuit all by itself, and just see if we still see that high frequency energy coming in. Now we're going to be using a vector network analyzer to look at the circuit behavior, because I'm going to remove this spark gap and kind of get that out of the way. But what I'm trying to do is simplify our circuit down to try to isolate where exactly this problem is. The other thing is, for this transformer, for making the measurements here, it's important to just keep this inductance really, really small. So ideally, this would not be affecting the circuit that much. We're kind of just getting just enough inductance to look into the circuit to see what's going on. But if this is too big, you're going to be actually messing with the performance of your circuit just when you try to make your measurements. So you want to keep that kind of as small as you can be. So yeah, that's what I'll do now. I'll kind of start disconnecting things and then look into it with a vector network analyzer. Okay, so what I've done here is I've now disconnected our input power to the circuit. So it's just sort of like a floating resonating circuit now, where I just have the capacitors hooked up to the transformer. I did replace the spark gap with a short circuit for right now, just for this analysis. So let's see what our VNA says. So we can see here that we're doing a scan, and we got a couple of resonances here. So we'll see right now we have two parallel resonances and a series resonance. Now, two of these are from the actual secondary part of the transformer. So we'll get inside of this transformer, there are primaries wound inside of secondaries, and the secondaries are coupled to the primaries. So when we start sending signals through the primaries of the transformer, we're going to get the feedback from the secondary as well. So even though we're not directly connecting to the secondary, we'll still get the resonant points and the impedance information displayed for the secondary coil. So you can see right now we have two parallel impedances or resonances given by these high impedance points, and one series resonance. Now if I just take my hand and kind of lay it across the secondary, you'll see that that kind of disappears and we just get our single resonant point here, and that will be our primary resonance. It's just kind of easier to view. Basically, when you have the two primary and secondaries resonating in the same neighborhood as each other, you get this phenomena, which I believe is called frequency splitting, where the resonances sort of separate from each other. So they kind of get shifted up and down in frequency so that the two can coexist in the same neighborhood. And that's because the magnetic field around these coils is a spatial field, so that actually needs some sort of space to exist in. And when you get the two coils resonating next to each other, they kind of fight for that space. So one will get pushed up and the other will get pushed down in frequency. So what we see here is a primary resonance along with our secondary resonance. Now the secondary resonance contains a series and parallel resonant point, whereas our primary only contains a resonant point. So I'll draw kind of what we have going on here on the whiteboard. So this here is our basic setup. here I just have the VNA hooked up across our capacitor. And like I said, I've just replaced the spark gap with a short circuit. And that is just basically, as far as the VNA is concerned, the capacitor is in parallel with the primary of our high voltage transformer. So we would expect to see a large parallel resonant point, which is indicated by the high impedance on the VNA. And that's what we see here. And let me just put my hand across the secondary again, just so we can see the display reduced to a single parallel resonance here on the primary. And now we got our secondary coming into the circuit again. So that's fine and well, but the problem that we were seeing is that we had this high frequency energy being introduced into our circuit. So what I'm going to do is I'm going to change the stop frequency for the sweep. I'll just put it at 10 megahertz, just so we can go far out. And we see we have a huge series resonance. So this is absolutely massive, and it just pretty much completely eclipses what we were seeing down below, you can see. So that does seem to be a problem. There's nothing in the circuit that would be designed, I guess, to give us a resonance at such a high frequency. You know, this circuit should not be in the megahertz frequency range. So there's some sort of parasitic effect happening, which is giving us a lot of high frequency. So even without the spark gap wired into the circuit at all, we were able to see that high frequency come into play. So something here is not quite optimized yet. We're getting a lot of frequency at such a high frequency. We're getting a lot of energy at such a high frequency content that our secondary coil isn't even able to respond to it. So we're sort of basically wasting a lot of energy at those frequencies, which we don't need. So let's try to figure out what is going on. Okay, so the first thing I tried was just disconnecting the capacitor bank and just direct connecting to the capacitor itself, because I know this thing is kind of clunky. So I thought maybe something about this design was creating all that parasitic high frequency, but you can see that we still have basically the exact same. So something else is causing the issue here. I think now what I'm going to try is just see if I reverse the position of the capacitor and the spark gap. Yeah, I know we don't have a spark gap right now, but if I short across here and place the capacitor in series with the primary, if we get the same high frequency introduced. Okay, so when I hooked up the circuit with the capacitor and spark gap switched in position, I was getting the same thing where this is you know, high frequency, which is overlaid on top of our lower frequency ideal primary current. So something else is going on, and you can see here I've gone and disconnected our input power again and hooked up our VNA to the circuit now with the spark gap installed, and our high frequency is back. So this is from 0 to 10 megahertz. So we can see our low frequency stuff here, but our high frequency content is back on the VNA. So we'll have to see about that. Okay, so now kind of starting to see what's going on here. So if you noticed the setup before, I had a lot of this this 14 gauge primary wire. It's stranded with this insulation material on the outside. I had a lot of this sort of just strewn about all over the place. And this may not seem like too big a deal at low frequency, but when you get a current impulse into this thing, even an inductance like this, it will behave like an inductor. And it looks like that's where all of our parasitic effects were coming from. So now I've tried to shorten the distance of cables used. I still have to connect with a little bit of cable here, but that's why the capacitor bank is up top now. just because I'm trying to decrease the amount of wire I need to make the connections. But I still have the same connections as before, where I just have the VNA hooked up. One side is going to this primary here, and the other is going to one end of the capacitor. So right now it's hooked up with the capacitor and the inductor sort of in series with each other. And the high frequency point just, it shifted big time to the top. So it seems like that is basically where all of our high frequency was coming from. So I need to get some different connections for all these different components in the circuit. I just need some low resistance, thick, bare copper wire because it looks like that's causing a lot of issues with adding high frequency components onto our primary currents. Okay, so I just finished making the new connectors for the circuit. So these are pretty much going to be making all the same connections that we had before, except now it's made with this thick bare 12 gauge copper wire, which is going to provide much less resistance and less capacitance. So there's going to be less energy storage capabilities in the dielectric field in our connection wires. And this is what we had before. So you can see that it's a much more compact or refined connection scheme. In order to do this though, I did have to change the arrangement a little bit. So I just kind of moved everything closer, and you can see we have a vertical capacitor bank now, but I do want to see what kind of effect this has on the response of this thing to the impulses. So I'm going to wire everything up and we'll see what it does. Okay, so this is what the new waveform looks like with the new circuit. As we can see, there is now a 3.3 nanofarad capacitor hooked up. So I've dropped the frequency a little bit. That's because I actually blew the last capacitor doing some testing. They're kind of dropping like flies, to be honest. But we can see the waveform that we got from this one. So we can see there is, still a pretty distinct low frequency wave here. It is about 250 kilocycles. And if we zoom in, we can see the high frequency signal that is overlaid on top of it. So we'll just see, that's about across the period. So it's somewhere in the neighborhood of 5-ish megahertz. This is not a totally accurate way to do this. See, just a little bit of change changes the frequency a lot, but it is still getting quite a bit of high frequency energy in the primary circuits. I don't know, maybe that looks better there as far as the amplitude of the low frequency wave. But okay, now we're gonna be looking at this using a slightly different method. So now I've just hooked up a probe to the end of this, and we're just gonna kind of approach the circuit with it. These are the kind of waveforms we're getting now with this. So these actually look a lot better. You'll see there's the high frequency overlay on top, which again, is expected with the usage of a spark gap. But now let's try to see some interesting things that we can observe with this. The first thing is that we see there's a much more distinct frequency of our oscillating circuit here. So let's just kind of approximate what frequency that's at. Just moving the cursors. About right there. So somewhere in the ballpark of high 200 kilocycles. And that's about what we would expect with the capacitances that I have in there right now. So that's pretty good. We do see the high frequency in there. Let's try to see if we can estimate what that's at. About 2 megahertz. Okay, so just by using a different method of getting this signal, we get some different characteristics. So it seems like maybe some of the stuff we were measuring before was just due to our measuring circuit, and maybe wasn't necessarily all due to the resonant circuit itself. But some more investigation into all that will be needed. One thing I do want to draw attention to right now is we'll see that from the start of this signal to where the 200 and something kilocycle signal approximately dies out, where the lower frequency signal dies out, we have about a 17-second pulse length. We do have some stuff over here, but it's mostly high frequency stuff. Our fundamental signal seems to have pretty much died out by then. So what I did to get this is I just went to the single mode, and I'm going to run the circuit for a little bit, and I'll just take little snapshots. It's going to be kind of hard to film this, so I'll just sort of, but basically what I'm going to do is I'm just going to hold this right here, and then I'm going to get a snapshot. I'm just going to have to go do it. I can't really film it. Okay. So that right there is what we just got. That one actually looks really good. Very strong fundamental signal. Pretty long tail. Let me just get one more. We'll see what it looks like. Okay, I'm just going to hold that right there. Okay, I got another one, and again, it looks pretty good. I mean, all things considered, that's pretty clean. So maybe this is a better way of actually obtaining the currents going through the primary. Let me now go and look at the output of the secondary. So I'm going to do the same kind of thing. I'm just going to fire the circuit up. I'm going to hold this thing right about here. And then we're going to kill it and take a snapshot and see what happens. This is all hard to do while I'm filming, so I'm just going to sort of do it. Okay. So I got a pretty good one there. That is what it looks like on the secondary. And you'll notice that it gets, it's pretty messy at first, but then it begins to kind of clean itself up. What this looks like in the beginning is we have different signals sort of fighting each other or overlaying on top of each other and creating these weird patterns. So we have the free resonance of the secondary, probably along with the driving frequency of the primary, which the two are not quite the same. So you get those weird overlay patterns where you have multiple sinusoids at once. But then once the intensity of the primary currents dies out and the secondary is allowed to freely resonate, we see it gets into a nice clean sinusoidal shape. So we can see if we approximate the distance of that messy signal, it's about 15 microseconds, which is about as long as the intensity of the primary of that fundamental frequency. So we can kind of see that the primary is fighting the secondary here at the beginning while it's energizing it, and then the secondary is allowed to freely oscillate after that. But this is a pretty good looking signal. So we can see here that our secondary is, let's try to get up close. Our secondary is running at about 350 kilocycles. So that's all good. I do think that what I was observing before with the spark gap was a mixture of the measurement circuit, or the way I was obtaining the measurements with that transformer hooked up to that core. That was probably creating some of that high frequency messiness that we were seeing. Also, the spark gap itself, I think, is just going to have some inherent high frequency content added to whatever signal you're trying to inject. But I think this is pretty workable at this point. I got a better idea as far as what's going on here. So we're just going to continue from here now. The one thing I will say that I'll probably try to do next is I've noticed that the bandwidth for the transformer here is pretty small, which means that it's very high gain over a small frequency band. And then if you go below or above that band, the signal level drops off very rapidly. So you need to do really fine capacitor adjustments in order to place yourself right at the point of maximum gain. And with this sort of setup, I'm really not able to do that at all. So what I need is some sort of variable high voltage capacitor where I can sort of fine tune things and get this thing running just right. And I think then we'll be able to get the types of discharge characteristics that we're looking for.